The next thing we're going to talk about is called dependent events. Now, two events, A and B, are dependent. They are dependent if one event affects the probability of the other. And the most common example of that would be, picking the cards from a deck. Up until now, we've always, assumed we put the cards back in and picked another one. But what if we kept that card out of the deck? Well, now there's fewer cards to choose from. So then the probability changes because your denominator, instead of being 52, because there are 52 cards in a deck, would be 51 if we don't replace that card. Now, the probability that B will occur, given that A has occurred, is called the conditional probability. And it can be written as the probability of B given A has already occurred. That's what that vertical line means. It's the probability that B will happen given that A has already occurred. Now, we have a formula for this. And again, sometimes the formula gets in the way of just thinking through the problem. So I always say, let's think about what we are asked to do and see if we can figure it out without a formula. So the probability of both A and B occurring is the probability of A times the probability of B given A had occurred. And it can also be written, if we divided both sides by the probability of A here in this left equation, it would be the probability of B given A would be the probability of A and B over the probability of just A occurring. And again, like these formulas we use in some instances, but a lot of times it's just easier to think about the problem. So for example, we got our standard 52 card deck, and we're selecting two cards at random. What is the probability that the first card is not a heart and the second card is a heart if A, you replace the first card before selecting, and then B, not replacing? So first, what's the probability that it is not a heart? The probability of A, it not being a heart, that would be 39 out of 52 because we have 13 of each suit. Not a heart would be the other 39 cards. And then it says that the probability of B, the second card is a heart, 13 out of 52. So when we learned about independent events, we can just multiply the probabilities. And like it says right here, if you replace the first card, then A and B are dependent events. So the probability of both happening would be 39 over 52 times 13 out of 52. So if we type that into our calculator, and I'm going to use fractions here. Oops. 39 over 52 times 13 over 52, and we get 3 over 16. So we have a 3 over 16 chance of selecting a non-heart and then a heart. Now, let's say if you do not replace the card before selecting the second one. Well, the probability of A is still 39 out of 52, selecting not a heart. But now the probability of B now is going to be 13, because we have 13 hearts out of 51, because I didn't replace that card, and by not replacing that card, I have fewer to choose from. So now I can multiply these together. So let's do that. We can just go back up here and change this 52 to a 51, and we get 13 out of 68. So 39 over 52 is 13 over 51 was 13 over 68. And if we converted those to percentages or decimals, this would be 0.191, and the other one would be 0.188. So it is a little bit more likely to have both these events occur if we do not replace the card. So if we go to the next page, that we look at these tables, this is what you're most likely going to see on an SAT conditional probability from a table. So it says the table shows the status of 200 registered college students. What is the probability that a randomly selected student is A, female, B, if the student was female, is a full-time student, C, is a part-time student, and D, is a male student given male given part-time student. So the probability of A, female. Well, how many females do we have? 80 plus 40 is 120. So 120 out of 200. And again, we want to reduce that fraction. Then we get 3/5. Now B says if female is a full-time student. So when it's saying if female, what that means is that I'm only looking at this row here. So my denominator is no longer 200. My denominator is the total number of females, which is 120. And then full-time, we have 40, which equals 1/3. So that part right here, if female, that's telling us, hey, we already know that the student is going to be a female. What is the probability that that female student is a full-time student? Then letter C just says is a part-time student. There is no condition through it. So part-time students, we have 80 plus 60, which is 140 over 200. And that will reduce down to 7 over 10. And then letter D, it says is a male given that they're part-time. So that means, again, we're assuming that they're part-time. So our denominator is going to be 140, and then the number of males in that is 60. So 60 over 140, and that reduces to 3/7. So you can see how the probability is different if you're just selecting or focusing on a subgroup here. We focused in on just the part-time students. What's the probability that that part-time student will be a male? All right, this problem. We have researchers surveyed 100 students on which superpower they would most like to have. This two-way table displays the data for the sample of students who responded to the survey. Find the probability that the student was male given the student chose flying as their superpower. So that means, again, I'm only looking at the flying row where the denominator is 38 and the probability that they were male, so 26. So 26 out of 38 reduces to 13 over 19 as your probability. Then find the probability that the student chose to fly given that the student was male. So that's the reverse of what we just did. A was find the probability that the student was male given that they chose flying as a superpower. B is find the probability that the student chose to fly given that the student was a male. So here are all the males. There are 48 total males, and the number that chose to fly were 26. So then it's going to be 26 out of 48, and we get 13 over 24. So again, like we could have used the formulas from the previous page, these formulas here, and in a way we're just thinking about them. Instead, we're not defining A and B and all that stuff. We're just looking at our information and thinking through it instead of using those formulas. And it goes by much quicker when you do that. Now, we can extend this to 3 or more events. So the formula for finding probabilities of dependent events can be extended to 3 or more. So let's look at these. Your teacher passes around a box of 10 red pencils, 8 pink pencils, and 13 green pencils. If you and 2 people in your group are the first to randomly select a pencil, what is the probability that all 3 of you select pink pencils? So let's go person by person. So the probability that the first person in your group, let's just say that it's you, selects a pink pencil. Well, we have 8 pink pencils out of how many total? 31. Right? Because if we add up the number of pencils, we have 10 plus 8 plus 13 is 31. Now, your group member then picks a pencil, and instead of there being 31 pencils, there are now 30 left because you took one, and you took a pink one, so instead of 8 pink ones being left, there are now only 7. Then the last person in the group, well, there's now 29 pencils left, and since you and one of your group members already took a pink pencil, the probability the number of pink pencils remaining is 6. So we'll multiply these 3 fractions together. So 8 over 31 times 7 over 30 times 6 over 29. And that gets us 56 over 4495, which we'll just make that a decimal. A lot of times I like to leave it as a fraction, but when the fractions are like this, where it's hard for us to comprehend, I'll make it a decimal. So 0.012, which is 1.2%. So very unlikely that all 3 of you will pick a pink pencil. Now, example 8 here. Find the probabilities of drawing the given cards from a standard deck of 52 cards. First with replacement, so we're putting the card back, and then without replacement. So we have the probability of a face card. Well, again, how many face cards are there? There are 12 face cards out of 52. Now I'm replacing them. So I'm putting the card back. So the probability of pulling a 7 is 4 out of 52. And then an ace is 4 out of 52 because there are 4 aces and 4 sevens. So we can multiply all of these fractions up. So 12 over 52 times 4 out of 52 times 4 out of 52. And we get 3 over 2197, which, if we make that a decimal, 0.001, which is 0.1%. So very unlikely that will happen. Now, with replacement, the numerators are going to stay the same, but as I pick more cards, there's going to be fewer and fewer left to choose from. So after I pull the face card, there are now 51 cards left in the deck. After I pull the 7, there are now 50 cards left in the deck. So if I go back up here and change this to 50 and change this to 51, okay, it's 6 over 4,225. And if we change this to a decimal, 0.0014. So if we compare that to 0.0013, it's not much more likely to happen when we replace it. So still 0.1%. So then letter B, probability of pulling a heart. So there are 13 hearts out of 52 times a club. There are 13 clubs out of 52. And then another club, 13 out of 52. Because again, we're replacing them. We're putting the cards back into the deck. So that means the denominator is always going to be 52. So we type this into the calculator. And I get 1 over 64. And you could have changed those fractions to 1/4. And then you probably could have done that in your head. And that's 0.015. So the probability of this happening is 1.5%. Now, the second part gets a little bit tricky. Yes, the first fraction is still 13 over 52 because I'm selecting a heart. Then selecting a club, there are 13 clubs out of now 51 cards because I'm not putting the first card back in. Now, for my third fraction, though, I want the probability of pulling another club. Well, in my second card, I've taken a club out. So there are only 12 clubs left out of 50. So it's like that pencil problem where once we took a pink pencil, that pink pencil is now gone, and we can't pick it again, so the numerator changed. And we get 13 over 850. And then in a decimal, that's, again, 0.015, which is 1.5%. If we were doing more decimals, then we would see that the probability does change slightly without the replacements, but it doesn't change very much because there are so many cards that we can still pick from. So that's it with conditional probability. It's really not that bad as long as you are thinking through the problem and not just relying on memorizing something and going with it. So thanks for watching. Make sure to like the video and subscribe.